the same state parameter, and essentially it'll have the same response to loading, both monotonic and cyclic. And Jeffries and Bean had suggested that although sort of intuitively you would think the state parameter of 0 is the boundary between contractive and dilative, it actually is a little bit on the dilative side, that roughly a state parameter of minus 0.05 is roughly the boundary between dilative and contractive behavior. Now, if we go back a little bit, the last webinar we talked about seismic liquefaction, and we looked at case histories, and this was based on the early work of Seed and Idris, over 40 years ago. And it's evolved as more case histories have occurred, and particularly case histories with CPT. But the concept was that you could use penetration resistance, either SPT or CPT, to evaluate the state of sandy soils, to evaluate the potential for liquefaction and estimate the cyclic resistance ratio. And then for siltier sands, this concept of a clean sand equivalent evolved. In the early days, it was the N160 with a correction to get N160 clean sand equivalent, and for the CPT, it's the normalized cone resistance, QT, QTN normalized, and then a clean sand equivalent. And so Catherine Wright and I had suggested a correction factor that was a function of the soil behavior type index. So the early corrections were based on fines content, but for the CPT, it was based on the soil behavior type index. And so the clean sand equivalent was this correction factor times the normalized cone resistance. And how that was developed was looking at the case histories of seismic liquefaction on the soil behavior type chart, and then drawing contours that would essentially separate sites that did liquefy from sites that didn't liquefy. The one on the right here is a little bit clearer. You can see that the clean sand equivalent contour bends over. And so that results in a family of clean sand equivalent curves. So you look at these curves. So the cyclic seismic liquefaction came up with a similar sort of conclusion, that when you looked in clean sand equivalent, you could have a clean sand that plots up here that would have the same response to cyclic loading as a silty sand with a smaller cone resistance and a higher friction ratio. So you have these contours of clean sand equivalent. Now, what's interesting is when you compare these two approaches, so if you, on the left, you've got the state parameter approach, essentially based on critical state soil mechanics and fairly comprehensive theory, supported by calibration chambers, numerical analysis, and frozen undisturbed samples. And then on the right, you've got these contours of clean sand equivalent that were based primarily on liquefaction case histories, of course, all seismic or cyclic liquefaction case histories. But when you compare the two, you can see they look remarkably similar. And that's very comforting for us to know that, over 30 years worth of work based on critical soil mechanics resulted in a set of contours that are not dissimilar to the over 40 years worth of work based on case histories. So it's very comforting to see that the theory and the case histories do come together. They do produce results that are somewhat similar. And from our perspective, the boundary line of between contractive and dilative state, which is roughly the state parameter of 0.05, minus 0.05, is roughly equivalent to the clean sand equivalent of about 70. And so you'll see later that we can use that previous approach that came out of seismic liquefaction to calculate the normalized cone resistance clean sand equivalent of 70, and that would define roughly the boundary between contractive and dilatant behavior. So this is just a slide that says that there is this link between the two, which is very, they produce very similar relationships. So if we look more generally, so here's the normalized soil behavior type chart, and you see I've drawn the contour for the state parameter of minus 0.05. Now I've shown a band here because it's not a precise location. There is some variability, as Jeffries and Bean have shown it. It will depend on factors such as in situ stress and stiffness and plastic hardening, etc. So it's not a perfectly well-defined line. And also I've shown down in the clay region, I've shown the boundary that would represent roughly the bounds for a normally consolidated clay, and arrows that show with increasing OCR, of course, the soils become more dilative. and with increasing sensitivity, the soils become more contractive. And so you see that there's some continuity between that boundary for sandy soils based on state parameter and the boundary that we traditionally would use for clay soils that would separate contractive and dilative material. Now, for reference, I've shown a line up here. Olsen and Stark had suggested a boundary. It actually sort of evolved from some work I'd done back in '95 that they converted over. And you can see that theirs really applies only to clean sand. It's a single value, so it only applies to clean sand. And so at clean sands, it completely agrees with the state parameter approach. But as you get into siltier sands, it needs to curve over as the state parameter relationship does. So this is just a reminder again that this clean sand equivalent of 70 is roughly equivalent to that state parameter of minus 0.05. So there are a number of case histories of flow liquefaction and been a number of publications over the last 25 years. You know, Seed, Professor Harry Seed did a paper in '87, then Ray Seed with Les Harder in '90, and then Stark and Mesri, and then Ride, and then Olsen and Stark, and then Jeffries and Bean did some, and then Olsen and Johnson sort of updated a little bit the Olsen and Stark, and then I did one in ASC 2010. So the number of case histories varies, but it actually depends a little bit on the definition of failure. And so there is some uncertainty with some of the case histories, particularly the ones that are seismically triggered, because there can be some uncertainty about whether or not it actually involved any strength loss, you know, true flow liquefaction, or whether or not it was just a lateral spreading and just a cyclic liquefaction and a buildup of large deformations due to lateral spreading. So some of the case histories, there's a little bit of uncertainty, but typically you get it down to about 30 or 40 case histories, and you know, more have been added in time. Some of them are very old, but some more recent ones. So when you look at the available case histories, in general, you find that the ones that definitely were strain softening, common features are the soil deposits are all very young. A lot of them were hydraulically placed fills, so you know, very young deposits, less than 100 years old. They were all very loose. They were generally non-plastic or at least low plastic. Plasticity index was very low, typically less than about 10, and quite often non-plastic. About 78, almost 80% of them were recent fills, 40% were hydraulically placed, 16% were tailings, and about half of them were triggered by earthquake, which also meant half of them were not triggered by earthquake. They were triggered statically. And several of the case histories, the triggering mechanism was very minor. I'll mention later about the Jamuna Bridge case history, and this was a very good example of about 36 submarine flow slides occurred during the construction of the Jamuna Bridge, and many of these were triggered by very minor disturbances. And what's also observed from the case histories is the failures tend to occur without warning. They tend to be rapid and can flow very large distances. So let's just look at a few. One of the most famous is the Stava tailings dam in 1985. 268 people died. Almost 200,000 cubic meters of material flowed down. So there was a relatively small tailings dam up in the valley. And it was a tailings dam that had existed for a number of years, but the mine had changed ownership, and the new owners didn't really control the flow of water into the tailings structure. And so there was a buildup in water level and a buildup of the phreatic surface in the upstream construction. And then suddenly it failed one day, and then very large failure occurred and flowed down the valley and went through several villages and killed 268 people. It's a very famous case history. And then a more recent one here in Hungary, some of you may recall seeing images on the news. This was a tailing structure. Here it is down in the right-hand corner, a relatively small tailing structure. And you can see the tailings are this sort of brown-red material. And the failure occurred at the corner, and then the tailings flowed out and went through several villages here. And it was about 700,000 cubic meters of material. And the video images that were caught on the news showed this essentially liquid tailings flowing through the village at quite a large velocity. And so when I looked at the available case histories, out of 36 that I was able to find, only 6 of them had CPT data, modern electric CPT data. And so the 6 case histories were the famous Nurlurk failure up in the Beaufort Sea, Jamuna Bridge, the submarine flow slide at the Fraser River that was written up in the Canadian Journal, Geotechnical Journal. There was a tailings failure at Sullivan Mines in British Columbia. And then there was a sensitive silty clay in northern Canada, a project I was involved in. And then, of course, there's the famous Lower San Fernando Dam in California. And so what I did is I looked at those 6 case histories because they had reliable CPT data. And what I did is I plotted the data. Essentially, I plotted a zone that represented all the data that was essentially capturing the mean plus or minus 1 standard deviation. And so you can see it plots typically as an oval. The dot in the middle is roughly the mean, and the oval is the mean plus or minus 1 standard deviation. And you can see that all of these case histories plot below that boundary line of a normalized cone resistance clean sand equivalent of 70. So basically that representing roughly that state parameter of minus 0.03, which would represent roughly the boundary between dilative and contractive. So sure enough, all these case histories plot on the contractive side. And that the boundary of 70 is a relatively conservative boundary. It's conservative in the sense that it's capturing the mean plus or minus 1 standard deviation. If you were to just capture the mean values, that number drops down closer to about a clean sand equivalent of about 50. Recently there was a fairly prominent failure in Tennessee Valley. It was the Kingston coal ash failure in December of 2008. And so on the left here is an aerial photograph of the tailings facility in April prior to the slide. And the slide again was in the corner of the tailings structure. And in the bottom right-hand corner is an aerial photograph shortly after the slide. You can see the extent of the failure and the flow. Now what I'm going to show you now is I'm going to show you some images that are all available on the website. So Tennessee Valley Authority is a government authority, and so everything is in the public domain from their website. And AECOM was hired to do a root cause analysis of the failure. And so all of the next few slides are essentially all taken from AECOM's data that's on the website, the Tennessee Valley Authority website. And AECOM did a nice job sort of generating a number of slides that tried to illustrate how the mechanism occurs. So you have the tailing structure, and here's the corner, and you can see that they had a smaller starter dike, and then they stepped back about 200 feet, and then upstream construction for the main tailings facility. And tailings were placed into the pond. And they estimated that the failure started in the corner, and then grew in size, and then eventually progressive failure started to eat back into the main pond, and then very quickly the whole pond essentially went. A very large amount of material flowed down the river, causing quite an environmental disaster. And so in cross-section, this is roughly the cross-section. There was an alluvial deposit, some natural clay, and then they had some small starter dikes, and then there were some fine-grained, what they referred to as slimes, so a fine-grained tailings deposit that initially got deposited probably underwater initially, and then the coarser fly ash got deposited, and then they, as I say, they stepped back and then started to build up. But the pond was quite close to the dam, and you can see a high phreatic surface. And they considered that the failure got started in the slimes, and then a failure plane developed, and then of course grew as it pushed the starter dams out as well, and then progressively moved back as the loose, coarse fly ash tailings started to fail as well. So they did an extensive study. They did sampling and some lab tests, and they determined the critical state line here. They refer to it as the steady state line, but essentially the same. And a lot of the samples were loose of critical state, and so when they loaded them in triaxial compression, you see they were strain softening with a very low ultimate strength. And so most of the field data was loose of critical state. So the coarse grain ash and the slimes were considered to be contractive and strain softening at large strains. What's interesting is the fine-grained slimes had a very high water content, between 40 and 140%. So relative to its liquid limit, the natural water content was much larger than the liquid limit, and so had very high liquidity indexes. So the liquidity index was ranging from 3 to 7, so well in excess of 1. And so, here's a nice plot that came out of Professor Mitchell and Soga back in 2005, sort of a nice plot that showed the relationship between liquidity index, vertical effective stress, and contours of sensitivity. And you can see that when liquidity index is greater than 1, then quite often you have high sensitivity, particularly at low confining pressure, around 1 or 2 atmospheres, sensitivities in excess of 10 and 20, etc. So the failure mechanism consistent with a very sensitive fine-grained slimes with very low undrained shear strength at large strains, but the sampling also indicating that the coarse-grained fly ash tailings was also contractive and strain softening. So here's some CPTs. I did a number of CPTs. I've just taken one. This is actually quite close to where the failure started. Now, admittedly, it was done after the failure, so it's not an ideal example, but it does illustrate some key points. And you can see that in the upper 7 meters, you've got a relatively coarse grain fly ash, very low tip resistance, friction ratio is low. Pore pressure is essentially hydrostatic, so you can see that it's essentially a free draining coarse grain material. And then you hit the slimes. In this case, the slimes are about 1/2 meter thick. So a dip in the tip resistance due to the soft slimes. Friction ratio picks up. Pore pressure didn't pick up too much, and then you've got the natural clay underneath and the alluvium underneath. And then if you run an interpretation, and if you just look at the peak undrained strength, the undrained strength ratio of the slimes is relatively low, but the sensitivity, there are spots that it jumps up very high. And then if you actually estimate the state parameter just based on clean sand equivalent, then sure enough, the fly ash is considered to be contractive over most of its depth, and certainly the slimes would be considered to be contractive. And so if you translate that over the way we did with the previous case histories, then most of the data would fall below that contractive line. And the coarse fly ash plot's a little bit higher up, but still underneath the boundary. And then the slimes plot on the contractive side. And the very weakest slimes are well inside the contractive, sensitive fine grain region. Now, another interesting case history, this is actually quite an old one that Professor Campanella and I